In this video, I'll be working through circuits using Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law to solve for voltages or currents around your circuit. So, let's go ahead and review what Ohm's law and Kirchhoff's voltage law and Kirchhoff's current law is first. So, Ohm's law, very simple. The voltage at a resistor, or the voltage drop due to resistor, is your current times resistance. So, if you had some resistor, the voltage drop basically means that if your resistor had a voltage drop of, let's say, 6 volts, and that means if the voltage on the left side is 10 volts, then the voltage on the right side is 4 volts. 10 minus 6 is 4. And that can be calculated by multiplying the resistance, or the amount of ohms in the resistor. So different resistors have different amount of ohms. You can have 5 ohms, you can have 5 kilo ohms, you can have 5 mega ohms, right? You can have 4.2 kilo ohms, right? And basically, you multiply ohms by the amount of current going through your resistor. You get the voltage drop due to the resistor. All right, how about Kirchhoff's voltage law? Kirchhoff's voltage law basically states that voltage drop is equal to the sum of the voltage rises. So, if you had some circuit and there's some loop that you can designate like so. So, there's like some box here. Maybe there's another loop here. And that means if you had positive and negative sides to these boxes, then you'd pick one of the loops. This is one loop, this is the second loop. So you pick one of the loops, you pick a direction clockwise or counterclockwise. Counterclockwise? What? Okay, and then you would basically pick determine whether the voltages are drop or rise. Well, in this case, if we go in the clockwise direction, this right here going upwards is in the clockwise direction. Upwards, downwards, left, right, whatever. But as you go in the clockwise direction, you go from negative to a positive side. So this right here, let's assign this V1, V2, and V3. V1 is a voltage drop. Okay? And V2 is a voltage, V1 is a voltage rise, since you go from negative to positive. V2 is a voltage drop, since you go from positive to negative. And V3 is a voltage drop as well, since you go from positive to negative in the clockwise direction. So you can pick clockwise or counterclockwise, it really doesn't matter. And you would do the same if you wanted to use KVL at this loop as well. Alright, what about KCL? Well, KCL basically states that the sum of all the currents into the node is equal to the sum of all the currents out of the node. So if you had some node like this, maybe you had resistors on the other side of these nodes, right? And all of these had currents going here, and there's a current going out here. And we assign this I1, I2, and I3. Then the current is going in, so the sum of the currents going in, the currents going into this node are the currents pointing into the node, so I1 and I2 are equal to the sum of the currents going out, and the only current going out is I3. So that means if this was 3 amps and I2 was 5 amps, then I3 must be 8 amps. So, for this problem, we want to solve the voltage at the resistor V of R, the current at the resistor I of R. The resistor has 3 ohms, and we want to solve the current at this voltage source. So sometimes you might see a battery instead of a voltage source, but for my future videos, I'm going to be using a voltage source in order to represent something that can create a current. Alright, let's go ahead and solve this. First things first, KVL. That's the first thing I noticed. And that's because in order to solve for this voltage V of R, we can do something very easy. We have the voltage of this voltage source, and we also have the positive and negative ends for both of these elements. So we can use KVL. Pick a direction, counterclockwise or clockwise. I pick counterclockwise. So, which of the voltages are drop and which of the voltages are rise? Well, if you go in the counterclockwise direction, V of R is a voltage rise, as you go from a negative to positive side in the counterclockwise direction. So V of R is a voltage rise. Well, how about the voltage source? Well, if you go to counterclockwise direction, you go from the positive to negative side. Therefore, this is a voltage drop. So the voltage at the source is 6 volts. Therefore, V of R is equal to 6 volts per KVL. So this is 6 volts. All right, well, now that we have that, we can use Ohm's law to solve for I of R, right? So Ohm's law Actually, if I were to write down all the steps, go ahead and put this in order for you guys. This is KVL. So Ohm's law is voltage is equal to current times resistance. So the voltage at this resistor is 6 volts. The current is unknown, but we have the resistance, 3 ohms. So if we divide 3 ohms on both sides, we get that I of R is equal to 6 divided by 3, which is 2 amps. So I of R is equal to 2 amps. Okay, well, now that we have that, we can use plain old simple KCL. Now, if you know what a series circuit is already, then you'll know that the current is the same throughout this entire circuit due to the fact that everything is connected end to end. And at the end, it's connected to ground, technically. But if you wanted to use KCL, there is a node here, right? A node is the connection point between elements. Technically, this entire top portion could be considered a node. But if I were to simplify this, the I of S is also here, I of S. I of R is also to the right side of this node. Therefore, currents in is equal to the currents out, I of R. So the current going in is I of S, and the current going out is I of R. Therefore, I of S is equal to I of R. And I of R is 2 amps, so I of S is equal to 2 amps as well. So for this problem, let's just solve for all the unknowns. So solve for all the unknown currents and all the unknown voltages on these resistors. Well, as you can tell, this is a series circuit. So that means all the currents will be the same. But for those of you that don't know that and only know KCL, I'll go ahead and explain that. So right here, let's label this current I of S. And I'm labeling it I of S because it's the current produced by this current source. And this current source is producing a current of 2 amps. So since there's a node here, these nodes are connection points between elements. This current source is an element, this resistor is an element, therefore this is a node, and there's nodes on every single corner here. So if we use KCL on each of the nodes, remember KCL's current into the node is equal to current out of the node. There's only one current going in, and there's only one current going out. Therefore I of S is equal to I of 1. And I of 1 is also going into this node, correct? Well, I of 1 is again a current going into this node, and I of 2 again is the only current going out. Therefore, I of 1 is equal to I of 2. And I of 2 is also equal to I of 3, and so on. Therefore, the entire current of this entire circuit is equal to the same thing. And that same thing is given by the current source, 2 amps. Alright, now that you know that, we have the currents on everything. Therefore, we can solve for all the voltages. Ohm's law helps us with this. Ohm's law is voltage is equal to resistance times current, V times IR, or V times RI, whatever. So we have all the currents, and we also have all the resistances, so we can solve for all the voltages. So let's go solve for V1. V1 is equal to 2 amps times 9 ohms. V2 is equal to 2 amps times 4 ohms. And V3 is equal to 2 amps times 6 ohms. Therefore, your voltages are 18 volts, 8 volts, and 12 volts. Let's go ahead and solve the unknowns for this. Alright, so first thing I notice, boom, we have the watts at this voltage source with the power absorbed. So using the power calculation, you can solve for the current I of S. But remember that this current is going the negative side first. So I of S, we can of course move I of S down into here as well if we wanted to. But since this current is going into the negative side of your source first, that means that you are using the not passive sign convention formula. Therefore, power is equal to negative voltage times current. Now, if current was going into the positive side of this element first, then it would just be positive voltage times current is equal to power. But in this case, not passive sign convention, I of S is going to be calculated like so. Well, in order to calculate I, we can isolate Let's actually move this up. We can isolate current, therefore power over negative voltage is equal to current. So the power in this case is negative 30 watts, and the voltage is 10. But we have to put negative 10 in this case. So that means current is equal to 3 amps. 3 amps. Well, if we use a little bit of KCL as well next. Let's put KCL up here actually. KCL, I of S is going into this node, I of 1 is going out. Therefore, I of S is equal to I of 1. So, I of 1 is equal to 3 amps as well. Go ahead and circle that. Alright, how about the voltage at this resistor? Well, remember, Ohm's law. So, Ohm's law is equal to voltage is equal to resistance times current. So, resistance at this resistor is 2 ohms, and the current is 3 amps. So, 2 ohms times 3 amps is equal to 6 volts. So we got 6 volts here. Okay, now that we have 6 volts, we can solve for this in many ways, of course. But let's go ahead and use KVL in this case. I like counterclockwise. So let's actually undo that. I'll pick counterclockwise. And let's go ahead and do some KVL. So, let's go ahead and determine which ones are the voltage rises and voltage drops. Well, if you go into counterclockwise direction, this 10 voltage source is a voltage rise since you go from the negative to positive direction. For 10 volts is on the voltage rise side. And the voltage drops go from the positive to negative. So if you go from the counterclockwise direction, V1 is from the positive to negative. Counterclockwise, V2 is positive to negative. Therefore, V1 plus V2 are in the voltage drop side of KVL. All right, well, now that we have that, what we can actually say is that, well, V1 is already calculated. It's 6 volts. Let's go ahead and remove this. And this becomes a simple algebra problem. That means V2 in this case is equal to 4 volts. 6 plus 4 is equal to 10. So we got 4 volts here. 4, let's write it in this place. There we go. All right, well, we can solve for I of 2 in 2 different ways. Either we can use KCL or we can use KVL. Let's go ahead and use KCL first. KCL or Ohm's law. Not KVL. What am I saying? Make some space. Let's go ahead and cut this off here. Then let's go ahead and use KCL at this node. Well, the KCL at this node is I1 is going into the node, correct? So I1 is here as well as here, and here as well. So I1 is going into the node, and also this 4 amp source is also going into the node, correct? If we follow along this path, we get that the current is 4 amps along this path. So 4 amps and I1 are going into this node, and I2 is the only current going out of the node. Therefore, 4 amps plus I1 is equal to I2. Well, the thing about I1 is that it's measured. We solve for I1. I1 is 3 amps here. So all we need to do is 4 amps plus 3 amps is equal to 7 amps. And this is equal to I2. So 7 amps like so. Or we can use Ohm's law. So let's make more space here. Ohm's law. So Ohm's law is voltage is equal to resistance times current. So if we just were to divide the voltage by the resistance, we would get the current, correct? Well, the voltage in this case is 4, and the current in this case is the resistance in this case is 4 over 7. And if we were to do this, we would simply get 7 amps. And both of these answers align properly. Now, if you do any of these laws and the answers contradict each other, like the answer from KCL and the answer from Ohm's law contradict each other, then your professor wrote a wrong circuit. Or you may need to do your calculations once again. Now, this circuit's quite simple. It just simply introduces you to the topic of what parallel circuits are, but it still tests your Ohm's law and your KVL and KCL knowledge. So let's go ahead and start this first. First off, KCL. let's go in the counterclockwise direction. I like counterclockwise. So counterclockwise, 20 volts is, let's start here. KVL. Oops. KVL. 20 volts is a voltage drop in the counterclockwise direction. Drop. And V1 is a voltage rise in the counterclockwise direction. So 20 volts is equal to V1. And if you do the same thing, if you do KVL again at this loop, you'll realize that V1 is equal to V2. Therefore, V2 is 20 volts as well. So when you have resistors in parallel, like so, and I'll have a video more in depth about that, then all the voltages at the resistors are the same. Right? That's a pretty cool thing you can do. You can also do something called current division, but I'll go more into that into another video. All right, now that we have all the voltages, we can simply solve for the currents. So let's go ahead and use Ohm's law to do that. Let's do Ohm's law here. So Ohm's law, voltage, we have the voltages, we have the resistance. Therefore, we divide voltage by resistance to get current. So I of 1 is 20 divided by 5, which is equal to 4 amps. So I of 1 is 4 amps. All right, how about at this 4 ohm resistor? 20 volts divided by 4 ohms is equal to 5 amps. Therefore, I of 2 is 5 amps. Right here, 5 amps. Okay, well, how do you solve for I of S, of course? Well, we recognize that this right here is a node. Technically, the entire top portion here is a node in itself. So now that we know that this top portion is a node, we can just do KCL here. So KCL is currents in is equal to the currents out. Well, the only currents going out of the top portion are the currents going downward. So the currents going downward and out of this top node here is I1 and I2. So I1 and I2 are going out. But I of S is going in. So I of S is on the opposite side of the equation. We have I1, we have I2. So we have 4 amps plus 5 amps. And this is equal to I of S, which is 9 amps. Therefore, I of S is 9 amps. And you have solved for this entire circuit. So, good job sticking through this entire thing. If you solved all the problems, you guys are amazing. But if you found this video helpful, consider subscribing and liking the video. I'm gonna hop on Grow a Garden.